Hello, my name is Shahriari, and this is a lecture in a series of lectures on undergraduate abstract algebra based on my book, Algebra in Action, a course in groups, rings, and fields. The subject of this lecture is the group of units of Z mod n Z, integers modulo n. Z mod n Z, I've defined it as the set 0 through n minus 1, where addition is addition modulo n. You add two numbers the usual way, but then you find the remainder when you divide it by n. That's a group. Subject of a previous lecture, this is actually a cyclic group of order n, meaning that it's always generated by one element, 1. If you take 1 and add it to itself, 1 plus 1 gives you 2, 1 plus 2 gives you 3, and eventually 1 plus n minus 1 gives you 0. It cycles back, which is why it's called a cyclic group. But the definition of a cyclic group is that it's generated by one element. And it's an abelian group. It's commutative. 3 plus 4 is the same as 4 plus 3. The theme of this lecture is that, what about multiplication modulo n? Can we get a group out of that? In this lecture, we'll define what we mean by the units of Z mod n Z, which will be denoted by Z mod n Z with a times on top. We will show that units of Z mod n Z with multiplication do form a group. Again, multiplication is not the normal multiplication of numbers, but multiplication modulo n. We will characterize the elements of the group of units in the sense that we will tell you what they are exactly. And because of that, we'll be able to figure out what the size of this group is. Along the way, we will prove that Z mod PZ is a field, and I will say what that is, if and only if P is a prime. First, let's talk about multiplication modulo n. You start with an integer greater than 1, and Z mod n Z again is 0, 1 through n minus 1. Multiplication modulo n just means that if you take two elements in Z mod n Z, then AB, their product, is going to be the remainder of the usual product, the usual AB product in the integers when you divide it by n. For example, Z mod 6Z is 0 through 5. And what's 3 times 5? 3 times 5 in our world is 15. But if you take all the 6's away from it, you take 1 6 and then another 6, 12 out, then you're left with 3. So 3 times 5 is 3 in this world. What about 5 times 5? In our world, 5 times 5 is 25. But the remainder of 25 when divided by 6 is 1. So 5 times 5 is 1 in this world. This operation is closed. The remainder will always be between 0 and 5. That's because of the division algorithm, but it's also intuitively clear. Does it have an identity? Is there something that when you multiply, nothing changes? And the answer is yes. 1 is the identity. 1 times anything is that thing. When we considered addition as operation, the identity was, of course, 0, not 1. But for multiplication, the identity is 1. What's the inverse of something? It's another element of your set that when you multiply them, you get the identity. Because 5 times 5 is 1, the inverse of 5 is 5. Does 2 have an inverse? The inverse of 2 means find me some element of the sets that when I multiply by 2, I get 1. We might just actually multiply 2 by everything and see whether or not we ever get 1. 2 times 0 certainly is not going to give us 1. It gives us 0. 2 times 1 gives us 2. 2 times 2 gives us 4. 2 times 3 is 0 again, because the remainder of 6 when divided by 6 is 0. And 2 times 4 is 2, and 2 times 5 is 4. When you get 2 times 5 is 10, the remainder when you divide it by 6 is 4. As you see, we never got 1. So 2 times nothing is 1. So in this world, 2 is not invertible. And that's an issue if you want a group, because in a group, we need inverses, which we don't have. We also need something else. We also need that it be associative. I have to prove to you that multiplication is associative. How far are we from a group? A group is a set together with an operation with 4 puny properties: closure, associativity, identity, and inverses. In this case, we have 3 of them. We don't have inverses, and that's a problem. And so we need a hack. And the hack is to throw the non-invertible elements out, and that happens to work. What we just decided is that Z mod n Z with multiplication is not a group. You don't get inverses necessarily. Well, actually, 0 will never have an inverse, because 0 times everything is 0. It's never equal to 1. But it seemed like, at least in some cases, some other elements don't have inverses either, and that's a problem. A unit is an element with a multiplicative inverse. Units are invertible elements. Units are things we like if you're interested in groups. What's the group of units of Z mod n Z? It's not the same as Z mod n Z, is some elements of Z mod n Z. Z mod n Z with a times on top, and we read that as the group of units of Z mod n Z, is those elements in Z mod n Z for which there is some other element such that AB is 1. Another common notation for this is UN, U for units, instead of Z mod n Z in parentheses with a times on top. One little fact will help us when we're looking at examples to decide what are the units. If you have two elements that are non-zero, but when you multiply them, you get zero, then neither of them is a unit. Why is that? Let's start with A, and let's say there was some x that if I multiplied by A, I got the identity. If xa is 1, then you can multiply by b on the right. So xa is 1, so xa times b is the same as 1 times b, because xa is 1. But xa times b, if you have associativity, and I promise that in Z mod and Z, we do have associativity of multiplication, you can, instead of xa times b, you can write x times ab. But ab is 0, and x times 0 will be 0. And so what you will get is 0 equals b, but we had said that a and b are non-zero, so b was non-zero. This is a contradiction. It says that there is no such x. There's no x that times a will give you identity. And the same thing with b with the same argument. Let's look at an example. Let's see what the units of Z mod 10Z are. Z mod 10Z itself is 0 through 9. Which ones of those are units? We'll notice that 2 times 5 is 0, because again, here we're doing multiplication mod 10. In number theory, you wouldn't write 2 times 5 is 0, because that just seems wrong. You would write 2 times 5 is congruent to 0 mod 10 to emphasize the fact that you're working modulo 10. In group theory, we think of it as if you're living in this group, this is your operation. This is how you multiply elements. So 2 times 5 is 0. Our point of view is that you're living in this world and you're not living in the integers. So forget about integers. This is how you multiply things. 2 times 5 is just 0. 4 times 5 is also 0. 6 times 5 is 0. And 8 times 5 is 0. So what? Well, that means that none of these elements are units. 2, 4, 5, 6, and 8 are not units because they got multiplied by something that was not 0 and they gave you 0. In ring theory, such elements are called zero divisors. On the other hand, 3 times 7 in our world is 21, but in Z mod 10Z is 1, which means that 3 and 7 are inverses of each other. 9 times 9 is also 1. And of course, 1 times 1 is 1. So these guys all have inverses. And so the group of units is 1, 3, 7, 9. I say group of units, but I still have to convince you that it's actually a group. It is a group, but in general, we need some things to be proven, including associativity. We'll get to that. But for now, the group of units of Z mod 10Z has 4 elements, 1, 3, 7, 9. Let's do algebra. Let's call 3 to be a. If we do that, then what's a squared? Well, a squared is 9. Then what's a cubed? A cubed is a squared times a, 3 times 9, and that will be 27, but mod 10 will be 7. A to the 4th, 81, will be actually 1. That means that every element of this group are just powers of a. The group of units of Z mod 10Z is of this form. It's E, identity, a squared, a cubed, and I have the relation that a to the 4th is e. I'm writing e for 1 because that's what I like to do for all groups in general. The group of units of Z mod 10Z is generated by a. Generated by a means that you look at all the words made up of a and its inverses, and in this case, that's just going to be a squared, and a cubed, but you have this relationship, a to the 4th is e. That's important because otherwise the group generated by a would just go on forever in both directions, a squared, a cubed, a to the 4th, but also a inverse, a to the -2, a to the -3, and so forth. But in this case, is just going to be 4 elements, E, A squared, and A cubed. This is a group of order 4. It has 4 elements, and it's a cyclic group. In a later video, we talk about cyclic groups more precisely and more detail. Cyclic groups are groups that are generated by one element. You can just start with one element, look at its powers and the inverses of those powers, an identity, and you get every element. This tells us that the group of units of Z mod 10Z is actually isomorphic to Z mod 4Z with addition. What does isomorphic mean? Isomorphic means that these two groups, as far as group theory is concerned, are the same. The definition is that if there's a relabeling, there's a way of saying this element corresponds to this element corresponds to that element, such that the multiplication tables of the two groups are the same. In this case, it's easy to see that. The group of units of Z mod 10Z has 1, 3, 9, and 7. I wrote them in the order that they were generated by A. And the cyclic group generated by A, where we have a to the 4th equals E. Bijection is very clear. 1 corresponds to E, 3 corresponds to A, 9 corresponds to A squared, and 7 corresponds to A cubed. And the multiplication table is going to be the same. So 3 times 9 is 7, and A times A squared is A cubed. The inverse of 9 is itself. The inverse of A squared is itself. Everything in the multiplication table, the way these guys multiply is the same as those guys multiply. What about Z mod 4Z with addition? Z mod 4Z with addition has 0, 1, 2, and 3 as its elements, and we're doing addition mod 4, not mod 10 anymore, but mod 4. The way we multiply these elements is exactly the same as we add these elements. In E, A squared, and A cubed, the operation is multiplication. but in Z mod 4Z with plus is addition. For example, 1 plus 2 is 3. That's the same as saying A times A squared is A cubed. 3 plus 1 is 0 here. A cubed times A is E. 7 times 3 is 1. So Z mod 10Z was a cyclic group of order 4. What about Z mod 8Z? What about the group of units of that? Again, 2 times 4 is 0, and 4 times 6 is 0. That tells us that 2, 4, and 6 are not invertible. On the other hand, 3 times 3 is 1, 5 times 5 is 1, and 7 times 7 is 1, and 1 times 1 is 1. So the group of units of Z mod 8Z also has 4 elements, just like the group of units of Z mod 10Z did. And they are 1, 3, 5, and 7. There are 4 elements. And one reasonable question would be if this is the same group, just in disguise as the one before. Let's try the same trick we did with the previous one. Let A be 3. Now, A squared, 3 times 3 is 9, but mod 8 is 1. If you go to A cubed, you get A back again. A to the 4th is 1 again. You are not never going to get 5 or 7 by just looking at products of A. So A is not generating this group for us. Well, maybe 5 will. But 5 squared is also 1. 5 times 5 is 25. Mod 8, you take 24 of it out, and you're still 1. What about 7? Well, C squared is also 1. And so none of them, none of A, B, or C, none of 3, 5, or 7, and definitely not 1, generate this group. What if we find some products? A times B is C. If you multiply 3 times 5, you get 15, but mod 8, that's 7. The group of units of Z mod 8Z consists of 4 elements, but they're not a cyclic group. They're not generated by one thing. They're generated by 2 things. You can write them as E, A, B, and AB. The last one you don't need a new symbol for. You can just write it as AB. And what are the relations? If you just write E, A, B, A, B, it's not really clear how you multiply those guys, but we know that A squared and B squared is E, and we also know BA equals AB. That's important so that if someone writes a word with A's and B's, because we know that this is a commutative group, an abelian group, you can move things and get all the A's together and all the B's together. If you want to write it with generators and relations, this is the group generated by 2 elements, A and B. There's nothing special about A and B. I could have had B and C or A and C, with the relationship that A squared and B squared are identity and BA is AB. In the previous one, the relationship was much easier. It was A to the 4th is E. I didn't need anything about moving things around because the only things I had were powers of A, and those automatically commute with each other. Whereas A and B don't necessarily commute with each other, so I have to specify that to be able to reduce long words into just those 4 elements, E, A, B, and AB. So this is a non-cyclic group of order 4. And in fact, now we know that there are at least 2 groups of order 4. Spoiler alert, that's all there is for groups of order 4, but that's a good exercise for you to do to try to see why that is. This group has a name. It's called the Klein 4 group. So the Klein 4 group is this group of order 4, which has identity and 3 other elements. All of those elements, when you square them, you get identity. And if you multiply any 2 of them, you get the 3rd one. Is the group of units actually a group? Of course it is. Otherwise, I wouldn't call it a group of units. But let's make sure that's the case. Well, it has an identity. Group of units consists of elements of Z mod NZ that are invertible. So every element has an inverse because we threw out everything that didn't have an inverse. Now, Z mod NZ with multiplication is closed. You multiply 2 things, you take the remainder mod n, you end up in there because of the division algorithm. But is the group of units closed? It doesn't follow from the previous one because we have thrown out some of the elements. So maybe if you take 2 units and multiply them, the result is not a unit. And it's one of the other guys, the guys you threw out. A little bit harder to prove is that the multiplication modulo n is associative. And I'm going to prove those 2 things first, then I'll come back to Z mod NZ and say some more things about it. Assuming associativity, we'll prove closure first. So what do we have? We have 2 units in Z mod NZ, 2 elements of the group of units, and we want to show that their product is also a unit. I've taken 2 invertible elements. I want to show their product is invertible. So how do you show that the product is invertible? The proof of the pudding is in the eating. I will come up with an inverse for AB. So A is invertible, so A inverse is the inverse of A, and B inverse is the inverse of B. What is going to be the inverse of AB? My claim is that the inverse of AB is B inverse A inverse. This is one of socks and shoes theorem. It says that if you put on your socks and then shoes, but then you don't like that and want to take them off, you first have to take off your shoes, then your socks. In this case, Z mod NZ actually doesn't matter because the multiplication is commutative. But this is true in general. If you take 2 invertible elements in any ring and multiply them, even if it's not commutative, the product is invertible for the same reason. Matrices, for example, is an example of that. Why is that? Why is AB inverse B inverse A inverse? How do we prove that B inverse A inverse is the inverse of AB? You just multiply them, see if you get identity or not. And AB times B inverse A inverse is the same as A times BB inverse A inverse. I'm using the associativity of the product. BB inverse is identity. A times E is A, and then A times A inverse is identity, and I'm done. So AB times B inverse A inverse was identity. That means they were inverses of each other. And that's what my claim was. AB does have an inverse. And so the group of units is closed. To prove associativity, I have to remind you of the division algorithm. Division algorithm says that if you have an integer greater or equal to 1, and then you have another integer m, and you take m and divide it by n, you get a quotient and remainder. Not only that, the quotient and remainder will be unique as long as the remainder is within a certain range, as long as the remainder is small. So there's unique integers q and r such that m is q plus r. So you're taking m, you're dividing by n, the quotient is q and the remainder is r. And as long as r is a non-negative and less than n, then q and r are unique. There's only one way to do that. If an m and an n walk through the door, and I try to divide m by n and find quotients and remainders like this, and you do it, we're going to get the same answer. One quick example, if m is 47 and n is 7, then there's various ways of writing this m equals qn plus r. That's not unique. You could write 47 equals 5 times 7 plus 12, or 47 is minus 2 times 7 plus 61, or 47 is 7 times 7 minus 2. You can write them in all kinds of different ways. None of these are the one that division algorithm is talking about, because the remainder needs to be non-negative. Well, it is in these two first cases, not in the last case, but it also has to be less than n, in this case less than 7, and in neither one of these two it is. In the last one it is, but it's negative, and that doesn't count. The only m equals qn plus r that satisfies the division algorithm is that 47 is 6 times 7 plus 5. And that 6 and that 5 are unique in the sense that anyone else who wants to take 47 and divide by 7 and get a small enough remainder, is going to come up with exactly the same equation. Now I'm ready to prove associativity in integers mod n when we use multiplication. This works for any elements of z mod nz. So if a, b, and c are elements of z mod nz, then in z mod nz, ab times c is a times bc. I said in z mod nz because you might forget that these have their own product. You might think that I'm talking about multiplying numbers. And multiplying numbers, we know they are associative, but this is in z mod nz. So what does this say? This says find ab, but find the remainder when divided by n. Then multiply by c, and then find the remainder when divided by n. Now over on this side, it says multiply b and c, find the remainder when divided by n. Then take that remainder multiplied by a, and then find the remainder when divided by n. And this claim is that these two things are going to be the same. Here's the proof. For the duration of this proof, there's a difference between a dot b and ab. AB is going to be when you take two numbers and multiply them. The normal thing you learned in 3rd grade. AB is that. But A dot B is going to be the product in Z mod nz, remainder of AB when you divide by n. When I say remainder, I mean a non-negative number less than n. If you take AB and divide it by n, what's the remainder? Well, by definition of A dot B, it is A dot B. By the division algorithm, AB is something, K1 times n, plus the remainder. And the remainder, remember, is A dot B. So this is one thing I have. AB is K1n. I don't know what K1 is, but something. K1n plus A dot B. I also have the same thing for BC. BC is some multiple of n plus B dot C. Again, B dot C is the remainder of the usual BC when you divide it by n. So what? The key to this proof is to think about the following question. What is the quotient and remainder of ABC when divided by n? And using the stuff we have, we can come up for candidates for that. First of all, I'm going to ask, what's ABC minus K1NC? Now look here, I have AB equals K1N plus A dot B. K1N was brought to the other side. You got AB minus K1N. And if you multiply it by C, you get A dot B times C. But whatever this thing is some number. And you can, again, by the division algorithm, divide it by n, and you get a quotient, K3, and a remainder. And what's the remainder? Well, the remainder is going to be A dot B dot C, which happens to be one of the things that we're interested in proving something about. So that's one thing we have, that if you take ABC minus K1NC, you get K3N plus A dot B dot C. I can do this also with this second equation I had with BC. Bring the K2N to the other side and multiply by A. So what is that? That's going to be the same as A times B dot C. Well, because B dot C is BC minus K2N. If you multiply it by A, you get A times B dot C. But again, using the division algorithm, whatever this guy is two numbers multiplied. You can divide it by n, you get a quotient K4, and you get a remainder. And the remainder is A dot B dot C. Because again, whenever you multiply two numbers, Fred and Joe, the remainder when divided by n is Fred dot Joe. In both of these, I can take the K1NC and K2NA and take them to the other side. In the first one, when I bring it to the other side, I can factor an n from K1NC and K3N. I will have something Q1 times n plus A dot B dot C. And I can do that for the second one, and I get ABC is some other number, Q2N, again, combining the terms that have n, plus A dot B dot C. When I look at these two equations, I see that I'm taking ABC and I'm dividing it by n in both cases, and I'm getting a quotient and a remainder. And these are remainders, and they're both non-negative and less than n. But the division algorithm says that the remainders are unique, that you can't find two different remainders, and therefore A dot B dot C is the same as A dot B dot C. I hope you went along with me. It's not a super complicated proof. There is some calculations you have to do, but it comes out really nicely. Now we know that this guy is a group because it's closed. We proved that. It's associative. We proved that. We already know it has a 1, and we picked the elements, units, the guys who were invertible. So this is a group. It's abelian. That means the multiplication is commutative, and so it's an abelian group. But what is its size, and can we characterize its elements? Those are the next questions we want to answer. The following theorem is a pretty important theorem. I told you what the elements of this group of units are those elements that are invertible. But what are those? Like if Z mod 18Z walks in the door, do I have to go through every element and decide if they're invertible or not? Or is there some way I can say which ones are not, which might help me in terms of finding the size of the group of units of Z mod 18Z, for example? The theorem is this. It says that the group of units is actually all those numbers between 0 and n minus 1 that are relatively prime to n. And that's what I want to prove. To do that, I want to first remind you about greatest common divisors. I had a whole video on greatest common divisors. If this is new for you, go watch that. If it's not, just follow through. If you have two integers, their greatest common divisor is also an integer, denoted GCD of AB, and has three properties. It's greater than 0. It divides A and divides B. When we put D line A, we read it as D divides A. That means that A is a multiple of D. D is a divisor of A. If you take A and divide it by D, you don't get any remainders. And D divides B, so D is a factor of both. And then it's the greatest common divisor. But the way I like to say that, instead of saying that D is the largest one among the divisors, I want to say that if some other C says, oh, I'm a common divisor, I divide A and B, then C will have to divide D. C will be a factor of D. So that's the way D is the largest, because all the other guys are going to be factors of D. This definition by itself doesn't say greatest common divisors exist. In fact, 0 and 0 don't have a greatest common divisor, but it's the definition we can use for all rings. The theorem about the greatest common divisor, the subject of a previous video, is that if you have two integers, and as long as one of them is not 0, you can't have both of them 0, but at least one of them be non-zero, then the greatest common divisor exists. And more than that, it's an integer linear combination of A and B. You can always find integers M0 and N0, so to write the greatest common divisor as a linear combination of them. Now, this fact is not true in all general rings, but it's true in some rings, and that will be an important part of when we study ring theory. An example, the greatest common divisor of 12 and 20 is 4. 4 is the biggest divisor that divides both of them, satisfies our definition of greatest common divisor, and you can write 4 as an integer linear combination. I never said that the integers have to be positive. 2 times 12 plus minus 1 times 20 gives you 4. This is a super useful fact, the fact that you can take a greatest common divisor and write as a linear combination. Two integers A and B are called relatively prime if their greatest common divisor is 1. In particular, that means that you can write some integer linear combination of them equal to 1. Now, in a positive integer, phi of n is going to denote the number of positive integers less than or equal to n that are relatively prime to n. How many integers between 1 and n, whose greatest common divisor with n is 1. This phi of n is called the Euler phi function or the Euler totient function. Again, phi of n counts the number of integers between 1 and n inclusive that are relatively prime to n. Now, n isn't going to be relatively prime to n, but 1 will be. For example, what are the numbers that are relatively prime to 10? 1, 3, 7, and 9. And so phi of 10 is 4. And by the way, we now notice that 1, 3, 7, and 9, those are exactly the units of Z mod 10Z. And phi of 8 is also 4 because 1, 3, 5, and 7 are the numbers that are relatively prime to 8. Let's get the show on the road and let's try to prove that if n is a positive integer, then the group of units consists exactly of the elements of z mod n z that are relatively prime to n. What are we trying to do? Z mod n z is 0 to n minus 1. We pick some element a in there, and what we want to show is that a is invertible if and only if the greatest common divisor is 1. There's two things we need to prove. We have two directions to prove. A is invertible, implies the greatest common divisor is 1. Greatest common divisor is 1, implies A invertible. Both of those need proof. Let's go with the first one. Assume A is invertible. What do I want to prove? I want to prove that that greatest common divisor is 1, but I don't know a priori that it is or not. I'm going to call it D. So let D be the greatest common divisor of A and N. I wanted to show that D is 1. Now, A is invertible, and so it has an inverse. Some elements of Z mod n Z, that's the inverse of A. That means A dot B is 1. When I write the dot, like in the previous proof, that's the remainder of multiplying A and B when divided by 1. So this product, A dot B, is in Z mod n Z, not in the integers. So B is the inverse. To say A dot B is 1 means that if you take AB divided by N, the remainder is 1. So that means that AB is NQ plus 1. This is division algorithm. You divide by N, you get a quotient, and you get a remainder. We said the remainder is 1, so AB is NQ plus 1. Rewriting that, 1 is AB minus NQ. But look at AB minus NQ for a second, and you notice that D divides A, D is a factor of A, and D divides N. Why? Well, because D is the greatest common divisor of A and N, so it must divide both of them. But if D divides A and D divides N, that means D is a factor of A and D is a factor of N, then that means that you can factor D out of this whole thing. And if D divides this side, then it must be a factor of 1. But what are the positive integers that divide 1? And the answer is 1. So D must be 1, and I'm done. So if A is invertible, it has to be relatively prime to N. Now we're going to the other direction. Assume the greatest common divisor is 1. Why is it invertible? And here's where things about greatest common divisor comes into play. So we want to show it's A invertible. It's because the greatest common divisor is 1, we know that 1 is an integer linear combination of A and N. This is the key issue. This is not so obvious. I mean, you have to prove this, and we proved it in a previous video, but you have to say that there's a U and a V, both integers, such that AU plus NV is 1. What's this one? The greatest common divisor of A and N. And as soon as you have the greatest common divisor, you know you can write an integer linear combination equal to that. So what? From this, I'm going to try to find what's the inverse of A. This says that AU is minus NV plus 1. This looks like you took AU divided by N, you got quotient minus V, and then you got a remainder 1. So maybe the remainder of AU when divided by N is 1. That will suggest that U is the inverse of A. So maybe U is just the inverse of A and we're done. There's a little subtle point here. We're not quite done, because it might be that that U that we found is a big number greater than N or less than 0. In other words, it's not in Z mod NZ. How do I deal with that? And there's a hack to that. If U doesn't work, it's just a little bit too big, just take out all the N's out of it. If it's too small, it's negative, add some N's to it. In other words, take U divided by N, you get a quotient and a remainder by the division algorithm. So do that. That remainder is going to now work. If you just multiply this by A and solve for AR, you get AU minus AQN. And instead of AU, you put minus NV plus 1, and you combine terms, and A times R is going to be minus AQ minus V times N plus 1. This R, we know for sure, is between 0 and N, is the multiplicative inverse of A in Z mod NZ, and therefore A is invertible. We started with the greatest common divisor B equal 1, and we found our inverse. We first found a supposed inverse U that was very close to being an inverse. You multiplied by A, and the remainder when divided by N was 1, but U might have been too large. And then if you find the remainder of that U when divided by N and follow through with the algebra, you will see that that R, that remainder, is the multiplicative inverse of A in Z mod NZ. One quick corollary is that the number of elements in the group of units is phi of N. So phi of N, the Euler phi function, tells us how many elements are in each of those abelian groups. Another little fact that we now know is that the only time you only throw 0 is if N is a prime number, because if N is a prime number, then everything less than N, other than 0, 1 through N minus 1, they're all relatively prime to that prime number. So all of them are units and all of them stay. And if the number is not prime, then its factors are not going to be invertible. To whet your appetite for the ring theory lectures, in general, if you have a set with two operations, in the case of Z mod NC, we have a plus and a multiplication. But if you have two operations, you say that you have a ring if With addition, you have an abelian group. Just think about Z mod and Z with plus. And with multiplication, you expect closure and associativity. And you also have to have distributive laws. If you have those, then you call that a ring. The typical example of a ring is the integers, the actual integers with plus and multiplication. But we just proved really that Z mod and Z with plus and multiplication is also a ring. And there are other ones, like, for example, n by n matrices with integer entries with addition and matrix multiplication is also a ring. Polynomials with integer coefficients is a ring, because again, in all of those cases, you can add and you can multiply, and they follow reasonable rules. In a ring, in general, you can add, subtract, and multiply, but not necessarily divide. And in Z mod and Z, that's exactly what we can do. We can add, we can subtract, and we can multiply, but we cannot divide. This is the final slide. A ring is a field if the multiplication is just nicer than what we said before. Before we just said closure and associativity, but the best we can expect is that if you just throw away zero, zero is never going to have an inverse, but if you throw away zero, then you get an abelian group. And that is a field. So in a field, you can subtract, you can add, you can multiply, and you can divide. Because every element is invertible, the only thing you can't divide by is zero. Some examples of fields are the real numbers, the complex numbers, and the rational numbers. But we just also proved that Z mod and Z with addition and multiplication is a field if and only if n is a prime number. So we have another example of a field, which is Z mod PZ when P is a prime number. The construction that we did in this video works in general, in the sense that if you start with any ring and look at the units of that ring, you get a group. These are some related videos that you might be interested. There were some prior videos where we talked about the addition of integers, division algorithm, the greatest common divisor. And there are some later videos, much later videos on ring theory that relate to the topic of this lecture. See you in the next one.